Classical information is defined using a thought experiment invoking the famous characters Alice and Bob. And the thought experiment goes as follows. Alice performs some random experiment. Say she's rolling dice. And she would like to communicate the result of her random experiment to Bob. Now the question is, what's the information content of that message? Yeah? And the question is, how can you quantify the information content of that message? The communication between Alice and Bob is restricted in the sense that Alice may only send bits to Bob. So she must encode the outcome of her random experiment in a string of bits. Yeah, so there's an encoding algorithm at work, and she encodes the outcome of her experiment in a sequence of bits. The random experiment that she performs has the outcomes of that random experiment have some probability distribution. And we assume that Bob also knows that probability distribution. So Bob knows the kind of random experiment that Alice is going to perform, and Bob also knows the underlying probability distribution. What Bob does not know is the specific outcome of the experiment, or if Alice repeats her experiment several times, then the sequence of outcomes, including the specific order. So if Alice rolls dice, for example, then, and these are ideal dice, then the probability distribution is simple. Every possible number of spots occurs with a probability 1/6. And Bob knows that. And Alice rolls the dice. Now here there are 5 dice. So let's say 5 times, or 5 different dice. So this is the number of trials. Here there are 5 trials of the random experiment. So this is all information that Bob has in advance. But what Bob does not know is the specific sequence of results. So the first die had 2 spots, and the next die had 4 spots, and so on. So that's new for Bob. And that's the kind of information that Alice has to send using a bit string. Now, at Bob's end, Bob receives the bit string. Bob has the background information about the probability distribution and the kind of experiment. And the bit string received should be enough for Bob to be able to reconstruct the sequence of outcomes of Alice's experiment. So the bit string obviously should contain enough information to enable Bob to reconstruct the outcomes of Alice's experiments. Classical information, or the amount of classical information, is now defined as follows. There's a quantity called the Shannon entropy. It's named after Claude Shannon, who developed this concept, I think, in the 1940s. And he defined classical information as follows. Alice and Bob try to use an optimal encoding, in the sense that they want to make the bit string as short as possible. They want to have maximum compression. Now, if Alice performs the random experiment n times, so there are n trials. So here, for example, let's say 5 times rolling a die. Then if she uses optimal encoding, maximum compression, then let's denote the number of bits that she needs, or the length of the bit string. Let's denote that by Sn. And the ratio, so the number of bits needed at optimal encoding to encode the result of n random experiment, of n trials, divided by the number of trials. Yeah? So that's the average number of bits needed for each trial in the limit of an infinite number of trials. That's defined as the Shannon entropy. So that is the average amount of information contained in the outcome of a single trial. From Bob's perspective, the average amount of information that he needs in units of bits for each trial that Alice performs. You may wonder why you need this limit n going to infinity, where this comes from. The reason is that it may be optimal and you may achieve the best compression if you don't encode each outcome separately. So in the sense that Alice rolls the first die, sees 5 spots, encodes that result in a bit string and sends it to Bob. And then she rolls the next die, sees 3 spots, encodes that, sends it to Bob, and so on. That's not optimal, or not necessarily optimal. It may be better for Alice to roll, I don't know, 10 times, 20 times, and first collect all the outcomes, and then encode the totality of all the outcomes and send this to Bob. To give you an example, if Alice rolls just one die, there are 6 possible outcomes. And in order to encode that, Alice needs 3 bits. Because with 3 bits, you have 2 to the power 3. So this is 8 possibilities for the bit string. And this is enough to encode the 6 possible outcomes of the die roll. It's a bit too much, actually. Yeah? It's not optimal, really. 2 bits would not be enough, because then you would have only 4 possibilities, and that's not enough to encode the 6 possible outcomes of the die roll. So Alice needs 3. Now, let's presume that Alice rolls the die 3 times. If every time she encodes each outcome separately, then for the first die roll she would need 3 bits. For the next roll she would need another 3 bits, and for the next another 3. So she would need a total of 9 bits. An alternative would be for her to first roll the die 3 times. Then for the totality of these 3 die rolls, there are 6 to the power 3. That's 216 possibilities. And this is smaller than 2 to the power 8. And this means that the outcome of 3 die rolls can be encoded with 8 bits, rather than 9. Yeah, so she has a better compression if she first collects results of various trials and then encodes them collectively. And of course, the longer the Alice waits and the more results she collects, the more compression she can achieve, and the greater the advantage over one-by-one compression. And the limit n going to infinity, that's the optimum that you can achieve. Yeah? And then on average, in this optimal scenario, on average, you need s bits per trial for the encoding. And that's the Shannon entropy. Yeah? So it's an idealized scenario. It's a limiting case, and that's the best you can do. And for the reason that I just described, the Shannon entropy is generally or can be smaller than the number of bits that you need to encode the result of the outcome of a single trial, the S1. Now, Shannon derived a formula for the Shannon entropy as a function of the probability distribution for the possible outcomes of a single random experiment on Alice's side. And we can approach that formula step by step if we first consider a few special cases. Imagine the random experiment of Alice is a simple coin flip with an ideal coin, so 50-50 probability. Then it's clear the two possible outcomes, heads and tails, are like the two values 0 and 1 of a classical bit. So in that case, there's nothing to be gained by sort of waiting until Alice has flipped the coin 10 or 20 times. But she can simply flip a coin, say if it's heads, she sends a 1, if it's tails, she sends a 0. Yeah? So in that case, the Shannon entropy is equal to 1. So for each trial, for each coin flip, she needs 1 bit. So the Shannon entropy is equal to 1. Let's consider another random experiment where each experiment is the simultaneous flip of r coins. Then there are 2 to the power r possibilities. But for the same reason as for the single coin, she can simply encode the result of each individual of these r coin flips with a single bit. So she needs r bits then for one collective flip of r coins. The first special case was the coin flip of an ideal coin with outcome probabilities 1/2 and 1/2. So we had a random experiment with outcome probabilities 1/2. And then we said the Shannon entropy was equal to 1. In the next scenario, we imagined that the random experiment is the simultaneous flipping of r coins. And then there are 2 to the power r possible outcomes of this combined flip. And we said in order to communicate that, Alice needs r bits. So the Shannon entropy is equal to r. And the probability for each outcome was 1 over 2 to the power r. Each of these possible outcomes was equally likely. I can write the expression for the Shannon entropy in a slightly different way. I can say the r, that's the same as the binary log of 2 to the power r. Or I can also say this is minus the binary log of 1 over 2 to the power r. This can be generalized, and I'm not going to do this here, but this is an argument involving continuity, that whenever you have a random experiment with d possible outcomes and each outcome is equally likely, so the probability of an individual of a particular outcome is 1 over d, yeah, so where d is the number of possible outcomes, then the Shannon entropy equals the binary log of the number of possible outcomes. Now, and this opens a possibility to find the general formula. And that the argument exploits the law of large numbers. Let's say the random experiment has the probability distribution with probabilities pi. I going from 1 to d, where d is again the number of possible outcomes. And let's say that Alice repeats the random experiment n times, so there are n trials. If n is large enough, and that's the law of large numbers, then the relative frequencies with which the various outcomes occur coincide with the probabilities. Yeah, I mean, I don't write this down in a mathematically very precise manner, but I just want to write down the basic idea. Yeah, you have the law of large numbers, which ensures that if n is large enough, then the relative frequencies will approach the probabilities. What Alice wants to convey to Bob is the specific sequence of the outcomes of her random experiments. Such a sequence is called typical if the relative frequencies of the various outcomes coincide with the probabilities of these outcomes. What the law of large numbers guarantees is that if n goes to infinity, then we can be certain that every sequence is typical. So for very large n, we may assume that all sequences are typical. We also know that all the possible typical sequences are equally likely. A specific typical sequence has the probability, well, the outcome 1 occurs with probability P1, and the outcome 1 occurs in the typical sequence where when you perform the experiment n times, then outcome 1 in a typical sequence will occur n times P1 times. So let's say you have a typical sequence where you have outcome 1 occurring in various places, and then you have outcome 2, say, occurring here, and so on. Outcome 1 occurs n P1 times, and outcome 2 occurs n P2 times, and so on. Now the probability of this particular sequence in this particular order is the probability that outcome 1 happens in the first trial, that's P1. And then whatever comes next, the corresponding probability times, and so on. And here again times P1, and so on. And when you multiply all these probabilities, then the factor P1 will occur n P1 times. So you will have P1 to the power n P1. The probability P2 will occur n P2 times. So you have that power. And so on, up to PD to the power n PD. That's the probability of one particular typical sequence. And in fact, that's the probability of any typical sequence. All typical sequences have the same probability, this probability here. Well, and at the same time, by the law of large numbers, you know, in this limit n going to infinity, all sequences are typical. All typical sequences have the same probability, and therefore the number of different typical sequences is simply equal to 1 over this probability. Now we said that on the previous page, we said that when you have a random experiment where all outcomes are equally likely, you have d different outcomes, then the Shannon entropy is simply the binary log of d. Alice and Bob agree that they let the number of trials become large enough so that for all practical purposes all sequences are typical. And only then Alice communicates the result collectively of all these trials to Bob. Let me call the number of typical sequences capital D. After she's accumulated the results of n trials and thus created a typical sequence, there are capital D possibilities. And to communicate these possibilities, she needs the binary log of D bits, according to the result on the previous page. Now this is the number of bits that she needs to communicate the entire typical sequence, and containing the results of n trials. And then per trial, this is the binary log of D divided by n. And this is by definition the Shannon entropy. And now we can see what this gives. If we insert the formula for capital D, this gives minus 1 over n, and then we have the binary log of this product. Now the log of a product is the sum of the logs. So this is minus 1 over n, sum over all I, binary log of pi to the power n pi. Now this is n pi log pi. And you see the number of trials cancels out here. And we are left with minus the sum pi log pi. And this is the general formula for the Shannon entropy. So I denote it here by the row in this formula in the box. I denoted, that's a shorthand for the classical probability distribution pi. It doesn't have a hat, so it's not a statistical operator, but it's a shorthand for the classical probability distribution. And this is the Shannon's formula for the entropy. For the classical information, it's this expression minus sum over I pi log pi. Perhaps you note that this is precisely this formula for the Boltzmann entropy in thermodynamics, in statistical mechanics. There's only the Boltzmann constant missing, and it's a natural log rather than a binary log. So up to proportionality, up to a multiplicative constant, the Shannon entropy coincides with the Boltzmann entropy. And that's not a coincidence, because the Boltzmann entropy in statistical mechanics tells you something about, it quantifies your ignorance about the microstate of the system. And in the same way, the Shannon entropy quantifies the amount of information that Alice has to send in number of bits to Bob in order to communicate the result of her random experiment. So it quantifies the amount of information that Bob needs in order to be able to reconstruct the outcome of the random experiment. So it quantifies the information that he misses about the outcome of the random experiment. Yeah. So it's a measure for Bob's missing information. In the same way that the Boltzmann entropy is a measure for our missing information about the microstate of a thermodynamical system.